Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss centrifugal pumps, their operation in basic terms like head, flow, and pressure. Most of the pumps we see, both at home and at work, are centrifugal pumps. And most of these pumps are driven by constant speed, alternating current motors. Head. Centrifugal pumps are dynamic machines, which means that they convert velocity into feet of head. To explain this concept of converting speed or velocity into feet of head, let's look at picture. This is the water intake section of the water treatment plant. Water flows from lake into a large concrete sump. The top of this sump is well above the level of lake. The line feeding the sump extends 3 miles out into the lake. The long line is needed to draw water into the plant, away from the pollution along the lakefront. The pipeline diameter is 12 feet. Water flows in this line at a velocity of 8 feet per second. 6 pumps, stationed atop the concrete sump, pump water into the water treatment plant holding tanks. One day, the plant experiences a partial power failure. 3 of the 6 pumps shown in picture shut down. A few moments later, the manhole covers on top of the sump blow off. Geysers of water spurt out of the manholes. What has happened? Hydraulic hammer. This is an example of water, or hydraulic, hammer. But what causes water hammer? Let's consider the change in the water velocity in the 3-mile pipeline when half the pumps failed. The velocity in the pipeline dropped from 8 down to 4 feet per second. Velocity is a form of energy, called kinetic energy. Energy can take several different forms. Heat in BTU. Elevation or potential energy. Kinetic energy in miles per hour. Pressure in PSIG. Electrical power in amperes. Work in horsepower. Acceleration. Chemical heat of reaction. About 250 years ago, Daniel Bernoulli first noticed 2 important things about energy. Energy in one form can be converted to energy in another form. While energy can be changed from one form to another, it cannot be created or destroyed. This idea of the conservation of energy is at the heart of any process plant. In the case of the water treatment plant, the reduced velocity of the water was converted into feet of head. That is, the elevation of the water in the sump suddenly increased and blew the manhole covers off the top of the sump. Momentum. If the length of the pipeline had been a few hundred feet, this incident would not have happened. It is not only the sudden reduction of the velocity of the water that caused an increase of the water level in the sump. It is also the mass of water in the 3-mile pipeline that contributed to the increased height of water in the sump. The combined effect of mass times velocity is called momentum. The mass of water in our pipeline weighed 160 by 106 pounds. This much water, moving at 8 feet per second, represents a tremendous amount of energy, about 500 million BTU per hour. If the flow of water is cut in half, then the momentum of the water flowing in the pipeline is also cut in half. This energy cannot simply disappear. It has to go somewhere. The energy is converted to an increase of feet of head in the sump, that is, the water level in the sump jumps up and blows the manhole covers off the top of the sump. Incidentally, this is a true story. Can you imagine what would have happened if all 6 pumps failed simultaneously due to an electric power failure? The result would be a dramatic lesson in the meaning of water hammer. Hydro accident in 2009. The hypothetical incident I've described above did actually happen, with tragic results. A new hydroelectric plant had just come on stream in Siberia. It was the world's 6th largest. An elaborate celebration tour was being held for the visiting dignitaries. Reportedly, a huge tree stump became lodged in the turbine blades of one of the giant water intake tunnels. The effect of the resulting hydraulic surge may be seen Wikipedia and YouTube. I've printed a few of the 100-odd photos available from the internet. I used them to frighten the engineers. 74 people were killed in the plant. Check the photos out for yourself. Of course, within days of the disaster, the Russians had modified the story. But one picture is worth 1,000 words. This is a picture of our washing machine as it was originally installed. Whenever the shutoff valve on the water supply line closed, water hammer, or hydraulic shock, would shake the water piping. The momentum of the water flowing in the piping would be suddenly converted to pressure. If the end of a piping system is open, as into a sump, then the momentum of the water is converted to feet of head. But if the end of the piping system is closed, then the momentum of the water is converted to pressure. To fix this problem, I installed the riser tube shown in picture. The top of the riser tube is left full of air. Now when the water flow in the supply pipe is shut, the momentum of the water is converted to compression energy. That is, the air in the riser tube is slightly compressed, as indicated by the pressure gauge I installed at the top of the riser tube. I invite you to compare my washing machine story to the accident at the Siberian hydroelectric plant. The lesson is that when we have fluid flowing in a very long pipe or channel, we have to consider what will happen when the fluid flow suddenly stops. We do not want the momentum to be converted into pressure, but into compression of a vapor or into potential energy. For example, on a long crude oil transportation pipeline, we might have periodic surge drums located along the line to safely accommodate a sudden stoppage of the flowing crude. An easy way to witness hydraulic surge for yourself is to install a pressure gauge at the suction of a centrifugal pump. Then shut down the pump. You will note a brief, but definite increase in the pump's suction pressure. This is the opposite of the effect I'll now discuss. Acceleration. Let us imagine that the 6 pumps in picture have not run for a few days. The water level in the sump and the level of lake will be the same. I now start all 6 pumps at the same time. An hour later, the water level in the sump is 12 feet below the water level in the lake. These 12 feet is called feet of head loss. If the pipeline is 3 miles long, we say we have lost 4 feet of head per mile of pipeline. If we look down into the sump, what would we see happening to the water level during this hour? Picture is a graph of what we would observe. The water level in the sump would drop gradually to 15 feet below the level in the lake. Then the water level in the sump would come partly back up to its equilibrium level of 12 feet below the lake level. Why? The loss of 12 feet of head as the water flows through the pipeline is due to friction, that is, 12 feet of head are converted to heat. But why do we have a temporary loss of an extra 3 feet? The answer lies in the concept of acceleration. Let's say you are driving your car onto the expressway. To increase the speed of your car from 30 to 65 miles per hour, you press down on the accelerator pedal. Having reached a velocity of 65 miles per hour, you ease off the accelerator pedal to maintain a constant speed. Why? Well, according to Newton's second law of motion, it takes more energy to accelerate your car than to keep it in motion. Referring again picture, the water in the 3-mile pipeline is initially stagnant. Its velocity is 0. An hour later, the water has accelerated to 8 feet per second. When you accelerate your car, the extra energy required comes from the engine. But when we accelerate the water in the pipeline, where does the extra energy come from? Does this extra energy come from the pumps? Absolutely not. The pumps are downstream of the pipeline and the sump. They cannot contribute any energy to an upstream pipeline. No, dear gentlemen, the energy to accelerate the water in the pipeline must come from lake. But what is the only source of energy that the lake possesses? Answer is elevation or potential energy. To accelerate the water in the pipeline to 8 feet per second requires more energy than to keep the water flowing at that same velocity. And this extra energy comes from the extra 3 feet of elevation difference between the water level in the sump and the water level in the lake. Once the water has reached its steady-state velocity of 8 feet per second, the need for this extra conversion of feet of head to acceleration disappears, and the water level in the sump rises to within 12 feet of the lake's level. Starting NPSH requirement. The need to accelerate the fluid in the suction of a pump is called the starting net positive suction head (NPSH) requirement. To calculate this starting NPSH requirement, let's assume suction line equals 100 feet. 8-inch suction line. Fluid equals water at 62 pounds per square feet. Initial velocity is 0. Final velocity is 10 feet per second. Then proceed as follows. Mass in line is 2,170 pounds. Change in momentum in line is 10 feet per second times 2,170 pounds equals 22,170 feet-pound, mass, per square seconds. If the operator increases the flow rate uniformly over a period of 100 seconds, the change in momentum is 22,170 feet-pound per square seconds divided by 100 seconds equals 222 feet-pound, mass, per square seconds. 1 pound mass equals 1 pound force times square second per feet. Therefore, the force needed to accelerate the water in the pump suction is 222 pounds, force. The area of the 8-inch suction line is 50 square inches. Therefore, the starting pressure loss is 222 pounds, force, divided by 50 square inches equals 4.4 psi or 4.4 psi times 2.31 is equal to 10.1 feet of water. Loss of suction pressure. The need to accelerate liquid in the suction line of a pump leads to a difficult operating problem, which occurs on startup. Just before the pump shown in picture is put online, the velocity in the suction line is 0. The energy to increase the velocity, that is, accelerate the liquid in the suction line, must come from the pressure of the liquid at the pump suction. As the pump's discharge valve is opened, the velocity in the suction line increases, reducing the pressure at the suction of the pump. The faster the discharge valve is opened, the greater the acceleration in the suction line, and the greater the loss in the pump's suction pressure. If the pressure at the suction of the pump falls to its bubble or boiling point, the liquid will start to vaporize. This is called cavitation. A cavitating pump will have an erratically low discharge pressure and an erratically low flow. As shown in picture, the bubble point pressure of the liquid is the pressure in the vessel. We usually assume that the liquid in a drum is in equilibrium with the vapor. The vapor is then said to be at its dew point, while the liquid is said to be at its bubble point. To avoid pump cavitation on startup, the experienced operator opens the pump discharge valve slowly. Slowly opening the discharge valve results in reduced acceleration of the liquid in the suction line and a slower rate of the conversion of suction pressure to velocity. Try this test. To illustrate what I have just explained, try this experiment. 1. Open the suction valve to a pump completely. 2. Crack open the case vent to fill the case with liquid. This is called priming the pump. 3. Open the pump discharge valve completely. 4. Push the motor start button. 5. Observe the pump suction pressure. You will see that the pump suction pressure will drop and then come partly back up. If the pump suction pressure were 15 psig to start with, it might drop to 12 psig and then come up to 14 psig. The permanent difference in the suction pressure between 15 and 14 psig is due to a 1 psi piping friction pressure loss. The temporary difference in the suction pressure between 14 and 12 psig is due to a 2 psi conversion of pressure to velocity or kinetic energy. To review, all the energy needed to accelerate the liquid to the suction of a pump comes from the pump's suction pressure. None of this energy comes from the pump itself. Or, as one clever operator at the refinery explained to me, pumps push, but they do not suck. Pump discharge pressure. Picture illustrates the internal components of an overhung, single-stage centrifugal pump. The term overhung refers to the feature that the pump has only an inboard, but no outboard, bearing. The inboard side of a pump means the end closest to the driver. The term single-stage means that there is only one impeller. Multi-stage pumps can have 5 or 6 impellers. The main components of the pump shown in picture are: shaft is used to spin the impeller. Coupling attaches the shaft to the turbine or motor driver. Bearings support the shaft. Seal prevents the liquid inside the pump from leaking out around the shaft. Impeller wear ring minimizes internal liquid leakage from the pump discharge back to the pump suction. Impeller accelerates the liquid. Volute converts the velocity imparted to the liquid by the impeller to feet of head. The impeller is the working part of a centrifugal pump. The function of the impeller is to increase the velocity or kinetic energy of the liquid. The liquid flows into the impeller and leaves the impeller at the same pressure. The location of the oval dot shown at the top of the impeller in picture is called the vane tip. The pressure at the vane tip is the same as the pump's suction pressure. However, as the high-velocity liquid escapes from the impeller and flows into the volute, its velocity decreases. The volute, which is also called the diffuser, is shaped like a cone. It widens out in the manner illustrated in picture. As the liquid flows into the wider section of the volute, its velocity is reduced, and the lost velocity is converted, well, not into pressure, but into feet of head. Feet of head. A centrifugal pump develops the same feet of head regardless of the density of the liquid pumped, as long as the flow is constant. This statement is valid as long as the viscosity of the liquid is below 50 to 100 cp or 200 to 400 SSU, Sevolts seconds universal. But, as process operators or engineers, we are not interested in feet of head. We are interested only in pressure. Differential pressure is related to differential feet of head as follows. Delta P equals specific gravity times delta H divided by 2.31, where delta P equals increase in pressure in psi, delta H equals increase in feet of head. In feet, specific gravity of the liquid is the density of the liquid relative to cold water. The increase in pressure increment P is also called head pressure. For example, if I have 231 feet of water in the glass cylinder shown in picture, it will exert a head pressure of 100 psi on the pressure gauge at the bottom of the cylinder. The head pressure would be proportionally reduced as the liquid becomes less dense. For example, 231 feet of kerosene, which has 0.75 specific gravity, would exert a head pressure of only 75 psi because it is lighter than water. Effect of specific gravity. Picture shows a centrifugal pump that may pump water through valve B or naphtha through valve A. Question: when water is pumped, the pump's discharge pressure is 110.4 psi. The pump's suction pressure is 10.4 psi. When naphtha is pumped, what is the pump's discharge pressure? Answer is the head pressure developed by the pump is delta P equals 110.4 minus 10.4 times 0.60 divided by 1.00 is equal to 60 psi, and the pump discharge pressure equals 10.4 plus 60 is equal to 70.4 psi. Next question: the pump is driven by an ordinary alternating current electric motor. It is running at 3,600 RPM. When we switch from pumping water to naphtha, what happens to the speed of the pump? Answer is nothing. An AC motor is a fixed-speed machine. It will continue to spin at 3,600 RPM. Next question: the pump is pulling 100 amps of electrical power. The flow rate is 100 GPM. If we now close valve B and open valve A, what happens to the amp load on the motor driver? Answer is the power demand will go down to 60 amperes or a form of electrical work. The units of work are foot-pounds. The feet of head developed by the pump is not affected by the specific gravity of the liquid. But the weight of liquid pumped is proportional to the specific gravity. If the specific gravity drops by 40% and the liquid volume, GPM, stays constant, then the pounds lifted by the pump drops by 40% and so does the electrical work. Last question, water is being pumped to a tank on a hill at 100 GPM. If we now switch to pumping a lighter fluid at the same rate, can we pump the lighter fluid to a higher elevation, only to a lower elevation, or the same elevation? Answer is the same elevation. Centrifugal pumps develop the same feet of head at a given volumetric flow rate regardless of the specific gravity of the liquid pumped. This means the ability of the pump to push liquid uphill is the same even if the density of the liquid changes. Pump curve. The feet of head developed by a pump is affected by the volume of liquid pumped. Picture is a typical pump curve. As the flow of liquid from a centrifugal pump increases, the feet of head developed by the pump goes down, as does the pump discharge pressure. A pump curve has two general areas. These are the flat portion of the curve and the steep portion of the curve. We normally design and operate a pump to run toward the far end of the flat portion of its curve. A centrifugal pump operating on the flat portion of its curve loses only a small portion of its discharge pressure when flow is increased. This is a desirable operating characteristic. A centrifugal pump operating on the steep portion of its curve loses a large portion of its discharge pressure when flow is increased. Pumps operating quite far out on their curve will have an erratic discharge pressure, as the flow through the pump varies. For one such pump, I have seen the discharge pressure drop from 210 to 90 psig as the flow increased by 40%. The flow through this pump was regulated by a downstream level control valve. The discharge pressure varied so erratically that the operators thought the pump was cavitating. Deviation from pump curve. Pumps always perform on their performance curve. It is just that they do not always perform on the manufacturer's performance curve. The dotted line in picture compares an actual performance curve to the manufacturer's performance curve. Why the deviation? The manufacturer's curve was generated using water. We are pumping some other fluid with a much higher viscosity. The clearance between the impeller and the impeller where ring is shown in picture may have increased as a result of wear. The impeller itself may be worn, or the vane tips at the edge of the impeller might be improperly machined. Perhaps the most common reason for the deviation is that the clearance between the impeller sides and the vertical sides of the pump case have increased, due to erosion of the interior of the pump case. This requires that the inside of the pump case be built up with the weld metal, and then machined back to the original manufacturer's tolerances. This procedure is a lot of work and is often neglected by the maintenance department, who do not consider this work to be part of their job description. If the pump is driven by a steam turbine, the pump speed could be lower than in the design. Available NPSH may be marginal. Watch my video on centrifugal pumps, suction pressure limits. Driver horsepower. Normally, increasing the flow from a centrifugal pump increases the amperage load on the motor driver, as shown in picture. Driver horsepower is proportional to GPM times feet of head. As shown in picture, as the flow increases, the feet of head developed by the pump decreases. On the flat part of the pump curve, the flow increases rapidly, while the head slips down slowly. Hence the product of GPM times feet of head increase. On the steep part of the pump curve, the flow increases slowly, while the head drops off rapidly. Hence, the product of GPM times feet of head remains the same or goes down. The response of the amp load on the motor driver is an indication of pump performance. A pump operating on the proper, flat portion of its curve will pull more motor amps as flow increases. A pump operating on the poor, steep portion of its curve will not pull more amps. If the manufacturer's horsepower per flow curve indicates that more horsepower is required as flow is increased, but the motor amp load is not increasing, then something is wrong with the pump. The amp meter for a pump is best located right on the start-stop box next to the motor. Unfortunately, more often, the only amp meter is located on the electrical breaker box, which is at a remote location. Impeller diameter. The pump impeller resembles a hollow wheel with radial vanes. The diameter of this wheel can be trimmed down on a lathe. If an impeller with a 10-inch diameter is trimmed down to 9 inches, it will have a new performance curve below its former performance curve. Both the flow and head of the pump will be reduced. Also, the amp load on the motor driver will decrease. As a rough rule of thumb, reducing a pump's impeller diameter by 10% will reduce the amp load by 25%. Not only will this save electricity, but the motor will run much cooler. Unloading the motor by 25% may increase the life of the motor windings by 10 years. When the control valve downstream of a pump is operating in a mostly closed position, the pump is a good candidate to have its impeller trimmed. Sometimes, the pressure drop across a control valve is so huge, greater than or equal to 100 psi, that it makes a roaring sound. The energy represented by this wasteful delta P is coming from the electricity supplied to the pump's motor. Hence, trimming the impeller also reduces wear because of erosion in downstream control valves. We frequently increase the size of impellers to increase pump capacity and discharge pressure. However, many chemical plants break the law when they do so. State boiler codes require that vessels and heat exchangers downstream of pumps be rated for the maximum pump discharge pressure at the maximum specific gravity that can reasonably be expected, unless the equipment is protected by a relief valve. Increasing the size of an impeller always increases its maximum discharge pressure. Hence, increasing the impeller diameter may be unlawful, depending on the maximum allowable working pressure, MAWP, of downstream heat exchangers. The MAWP is shown on the exchanger nameplate. Increasing the size of the impeller by 10% will increase the amperage load on the motor driver by 30%. For many process pumps, this would require a new motor and breaker to support the larger impeller. Trimming the pump impeller on a lathe also requires the reshaping of the tips of the impeller vanes. Most often, this requirement is ignored, and the revamped pump operates below its expected curve. Rather than worry about these fine points, it is best to order new impellers directly from the manufacturer. Installing a larger impeller may require an upgrade in the pump bearings and the mechanical seal. While it is good practice to purchase a pump with a seal and bearings rated for the maximum impeller size, some pumps can have bearings and seals rated only for their purchased impeller size. For process people, the only practical method to check that a pump's seal and bearings are suitable for the larger impeller is to check with the manufacturer. Drilling pressure balancing holes in the hub of the impeller helps to reduce the extra strain on the bearings of a larger impeller. Sometimes installing a full-sized impeller causes the pump to vibrate. This happens because of a disturbance to the liquid as the vanes spin past the volute or diffuser, that is, the case outlet opening. Exxon had at one time a standard of keeping impeller sizes at not more than 92% of the full impeller diameter. This seems a conservative practice to me. We have usually kept impeller sizes in our revamped designs 0.25 to 0.5 inches below maximum. I don't recall anyone complaining that such pumps vibrated as a result of the enlarged impeller. On the other hand, for a new installation, now that we have learned of the Exxon standard, we plan to follow it in our process design work. Impeller rotation. Motor-driven pumps often are found running backward. If the motor is wired up backward, this is called reversing the polarity of the leads. The pump will run with the impeller spinning backward. This will reduce the pump's discharge pressure, sometimes by a little, 10%, and sometimes by a lot, 90%. It depends on the design of the impeller. You cannot see the direction of rotation of a pump, but if you touch a pencil to the spinning shaft, you can feel the direction of rotation. The correct direction of rotation is indicated by an arrow stamped on the top of the pump case. There are right and left-handed pumps. So, two otherwise identical pumps may have opposite directions of rotation. A pump impeller will spin backward because the motor wiring is connected incorrectly. I'm referring to a three-phase motor. For a single-phase motor, the wiring connections may be reversed without affecting the direction of rotation. In North America, they use 60 Hz electric power and motors operate at 1,800 RPM, single-phase, or 3,600 RPM, three-phase. In Europe and Asia, 50 Hz electric power is the standard. Single-phase motors spin at 1,500 RPM and three-phase motors at 3,000 RPM. An engineer was working on a project to relocate a U.S. process unit to Cyprus. The project met a merciful death when he explained that a 100 horsepower American pump, 60 Hz, would only produce 58% of pumping power when connected to a European, 50 Hz, motor. That is 100 horsepower, cube root of 50 divided by 60, equals 58 horsepower. According to the affinity or fan laws, work or power varies with speed, cubed. It is possible to rewire a three-phase motor into a single-phase motor, and thus reduce its speed from 3,600 to 1,800 RPM. Then its power consumption would drop by a factor of 8. An engineer done this once at a refinery, which had a hugely oversized sulfur plant incinerator air blower. For most projects, a more typical option would be to retrofit the motor for variable speed operation, using frequency control. However, not all motors are amenable to frequency control, which is a relatively expensive option. Feedback from clients that have retrofitted pump drivers with variable speed AC motors is often unfavorable. Effective temperature on pump capacity. If we wish to increase the capacity of a centrifugal pump, should we make the liquid hotter or colder? Let's make a few assumptions. Cooling the liquid will not increase its viscosity above 30 or 40 centistokes. We are pumping hydrocarbons. Cooling many hydrocarbons by 100 degrees Fahrenheit increases their density by 5%. The pump's motor is somewhat oversized. On this basis, cooling the liquid by 100 degrees Fahrenheit will raise the pump's discharge pressure by 5%. If the pump is developing 1000 psig of differential pressure, cooling the liquid by 200 degrees Fahrenheit will increase its discharge pressure to 1100 psig. If the discharge control valve is now opened, the pump's discharge pressure will drop back to 1000 psig as the flow increases. The discharge pressure drops because the pump develops less feet of head at a higher flow rate. To summarize, the specific gravity of the liquid has increased by 10%. The feet of head of liquid has decreased by 10%. Since delta P is almost equal to specific gravity times feet of head, delta P remains constant. But the lower required feet of head permits the pump to operate further out on its performance curve. This produces more volumetric, GPM, flow. It also requires more work to pump the greater flow. So, we have to have sufficient excess amperage on the motor driver to accommodate this maneuver. But that is the price we pay for expanding the pump's capacity without increasing the impeller diameter. Of course, the larger diameter impeller would also require more motor amperage. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.